So we want to start today by finishing some problems we didn't have time to get to last time. So where did we finish last time? Well, it's this idea that if you have a tangent plane, it locally can approximate the function. And so if I want to understand what's happening nearby a particular point, I can say, okay, let me find the tangent plane to that particular point and see what happens on the tangent plane. So we finished with an example which had z equals f of xy. Here's a slightly different one. So suppose that we're on a surface. So x squared plus e to the xz plus yz is 2 plus cosine xy. And we have that there's this point on this surface, 0, 1, 2. And we're told, well, what do we want to do? We want to estimate y for this relationship, given that we know x, which is 0.04, and z is 1.97. So another way to say this is we say, well, look, there's this point here, 0, 1, 2, and I want to find a point where it's 0.04 something 1.97. Okay, so the question is, what goes here? Well, to find the exact value, you'd have to solve, plug in x is 0.04, z equals 1.97 into this relationship, and try to find y. Now, you probably couldn't find it exactly, but you could find it up to high precision. What we're going to do is find it up to low precision. All right, well, how do we do that? Well, of course, one thing to say is, well, I have this 0.04, 1.97, it's really close to 0 and 2. So it's like, okay, well, super low precision, it's about 1. Well, we want to do a little bit better than that. All right, so how do we do better than that? Well, we say there's a tangent plane to this surface, and we use the tangent plane to be an approximation for the surface. Now, because we did a problem last time, we can just recall it. The problem we did last time is we said, suppose you have that surface. In fact, it's the exact same surface. This is recycling. Yes, mathematicians are environmentally friendly. We recycle. All right, so it's the same surface, and lo and behold, the same point, 0, 1, 2, and so we can say, aha, what we can say is the following, that the tangent plane is 2x plus 2y plus z equals 4. So now, instead of saying, let me figure out what's going on with this complicated function, it truly is a complicated function. It's an implicitly defined surface. Instead of doing that, what we can do is we can now use the tangent plane. So that's how we get our approximation. So we say, all right, well, what is y? Well, I can solve for y here. I can say that y would be equal to 4 minus z minus 2x all over 2. Okay, so that would be what? Well, be 4 minus 1.97, because that's z, minus 0.08, because that's twice x, all over 2. Well, now we have to do a little tiny bit of math. But this is math we can handle. It's not so bad. If we look at this and stare at it for a while, we say, well, what is that? Well, it's really 4 minus 2.05, because I can combine those two together. And if I take 4, subtract 2.05, what do you get? Well, you get, by my computations, 1.95. Okay, of course, then we're going to divide that by 2. And if you take 1.95 divided by 2, well, okay, you get more stuff. I believe you get 0.9975. Am I close? No. 975. Now, that's a really big point. 0.975. All right. So, that says a good estimate for y is 0.975. That's it. All right. So it's not a very complicated idea. You just have to know how do you start. That starts Sorry, excuse me, that's true for a lot of the problems in calculus. The actual steps aren't very hard. It's what steps am I supposed to be doing? All right, well, practice. Practice, that's how you figure it out. All right, one more problem before we move on to today's topic. Your company is the leader in widget manufacturing. What's a widget? It's a small cylinder. And they're supposed to have the following. So we'll draw a picture to help us visualize here. So I have a cylinder, and it's supposed to say that it's a radius of 2 inches and a height of 3 inches. But of course, no widget machine is perfect, and there are always small defects. So this is actually realistic. Look, you're going to make parts, but nothing can be perfectly reproduced. So there's always defects. And so the question is, what do you do? Well, we have to say that the volume of our widget can have a tolerance. So the tolerance is within. So it says, I can have my volume vary by as much as pi. All right. And it's known that the height can vary up to 0.1. And the question is, how much can we allow the radius to vary? So given that we have some tolerance already for the height, how strict do we have to be about the radius to stay within our bounds? Now, we can get a pretty good estimate by using calculus. So let's start with some basic facts. How about the volume of a cylinder? That's pretty basic. What is that? Pi r squared h. So volume is pi r squared h. And what I'm going to think of now is volume as a function of two variables r and h. So instead of x and y, think of r and h as our variables. And if we go through and look at the tangent plane for volume, we can rewrite it in the following way, namely that the change in the volume is approximately partial v partial x change in x plus partial v partial y change in y. This is one of our basic fundamental ideas, that namely we can estimate how things are changing by using these planes, linear approximations. Now we just need to sit down and identify some things. So change in volume, what we can think of is, this is how much I'm willing to tolerate. All right, how precise do I need to be? Well, we're within pi. So change in volume is up to pi. So we're going to say change in volume pi. Whoops, and I said x and y. Oh my gosh, that's a typo. I should have said r and h. It's a very fancy h on the end. Okay, cursive h. All right, so partial v, partial r. What is partial v, partial r? The derivative of v with respect to r. 2 pi rh. Delta r. Now, delta r, we don't know. We're trying to estimate that. Partial v, partial h. What is that? Pi r squared. Delta h. Okay, how much can we tolerate? What are we willing to give? 0.1. So again, that's a tolerance. This is within 0.1. Okay, so we have that pi is approximately 2 pi rh delta r plus pi r squared times 0.1. But of course, we know r and h because we were told r should be 2 and h should be 3. So 2 times pi times r times h, well, that would be 2 times pi times 2 times 3, which would give us 12 pi delta r. And then pi r squared, well, that would be 9 pi times 0.1. Oh, sorry, 4. Ah! All right, 4 pi. Thank you. Whew. Good. I was worried. All right, now what happens? Other than I stopped making errors.
Solve for delta r.
Solve for delta r. It's the only thing we don't know. It's how much can we tolerate for delta r? Well, notice everything has a pi. So we can get rid of the pi's. All right. So then what happens? Well, I can think of this as 0.4. I'll move it across. Right now it's 1. So if I subtract 0.4, that leaves me with 0.6 is approximately 12 delta r. And then divide by 12. Now if you take 0.6 and divide it by 12, what do you end up with? You end up with 0.05, which means that we have to be a little precise with the radius. We're willing to go up to 0.05 off, and that's about as far as we can tolerate. If we go any more, we're not going to be able to keep our quality control in place. And we want to make sure we have a quality product. All right. So that's the end of last lecture. And now, in the few minutes we have remaining, plenty of time. We're going to start today's lecture. Now, our goal, just to sort of foreshadow what's about to happen, is we're really moving in towards the fun part of derivatives, which is optimization. So pretty much everything from here until the exam is about optimization. And it's not going to feel like it today, but I promise you that what we do today is to set up something really cool for the next session, which is going to be important for optimization. So what are we doing today? Well, today we want to talk about the idea of how do we get better estimates, or at least how do we understand things better. So we already know that our tangent planes are great for estimating. And so if I have a function, I can say, look, my function can be approximated by my tangent plane, f of ab plus partial f partial x at ab times x minus a plus partial f partial y at ab times y minus b, plus an error. Now the reason I put the word error here is notice that this is an equal sign and not one of these approximation symbols. So the equal sign says, all right, everything off that I am goes into that error. So what we want to do is try to get a better handle on that error. Now, we say our function is a nice function, which in calculus means it's differentiable, if that error is small. So in particular, if I'm at a point xy, which is very close to a point ab, so if the distance is small, we want the error to be small. That's what we mean by having a nice differentiable function. Well, what can we do? We'd like for this error to get smaller. All right, so that's our goal. And how are we going to do that? Well, we're going to take a step back. Memory lane, Calc 2. And this is about the only part of Calc 2 that you'll need to know. Taylor polynomials. Now, I can see the giddy laughter like, oh, yes, my favorite part of Calc 2. Okay. Well, don't worry. We're just being very gentle. We're just going to touch lightly on the subject. So what's the idea of a Taylor polynomial? Well, the idea is that functions can be well approximated by polynomials. But what we're doing with those polynomials, we're not just doing anything. What we mean by well approximated is we're going to mimic the behavior locally. And the behavior locally is driven by what's happening to determinants. So we're just going to look at sort of a sequence. So one way to approximate the function at a is to say, well, look, let's just look at the function at a plus a rather large error, which is to indicate that when I write it this way, I'm thinking, oh, my function f of a, this is like a constant. Most functions don't behave like constants. So the error is pretty substantial. Even close by, it's not a great approximation. And then we said, hey, there's this thing called a tangent line. So that's f of a plus f prime of a times x minus a. And now you'll notice the error has gotten smaller because we better approximate. We now have a better approximation to what the function is doing, and so we get a better guess, better error control. And now, the second order Taylor polynomial. What is it? Well, you start with your tangent line. You got your f of a, your f prime of a times x minus a, and then you add on to that the second derivative at a divided by 2, x minus a squared. So what you're doing is you're saying, I want to match the value of the function, I want to match the value of the derivative, and I want to match the second derivative. And here's the key thing. See how our error shrank when we went from just a constant to a line? It shrinks more when we go from a line down to this parabola, which is what we have when we do a second order Taylor polynomial. So the reason it's shrinking is we are now capturing more of the behavior of the function. So it does a really good job. Now that's the part we have to remember. We don't have to go any further. In Calc 2, we then said, why stop there? Keep on going. But for us, we're going to be, let's stop there. This is all we need. All right, so what are we going to do? Well, we're going to do something really similar, which is we're going to say, look, let's make up a polynomial function, multivariable polynomial, and our goal is to match the small derivatives. And in particular, we're going to match it all the way up to the second order derivatives. And we call it the second order Taylor polynomial. So here we go. Our function says I could approximate it by just the constant term. That would be f of ab. That would be if I'm matching the 0th order derivatives, and the 0th order derivative is just the original function. But I can do better if I say, well, let's also match the first order derivatives. Okay, so that's a better approximation. If we stop here, what do you have? Well, it's not a line. We're in 3 dimensions. It's a plane. What plane? It's a tangent plane. So Taylor polynomials are sort of a generalization of the tangent plane, because we're going to go one more layer. So far, that stuff we've done before. Here's what we add. We're going to add second order derivatives. So what we do is we add in 3 terms. So we have 1/2 times the derivative f sub xx. Remember, that's the second order derivative, or we took derivative with respect to x both times. At ab times x minus a squared. The mixed derivatives fxy at ab times x minus a y minus b. And then 1/2 f sub yy, that's the second order derivative with respect to y twice, evaluated at ab times y minus b squared. Okay, and so that's the second order Taylor polynomial. So we want to take some time to work with this, do some examples, and understand this a little bit better. Now, a couple of things you might wonder looking at this. Why does this have a half? Well, why did that have a half? Same answer is when we take the derivative twice, notice what happens when I take the derivative the first time. What happens to that square, that x minus a squared? When you take a derivative, the 2 does what? Goes down. So you have to have something to compensate. So that's why there's a half there. So that when you end up taking the second derivative with respect to x twice, everything will vanish except for this f sub xx at ab. So the Taylor polynomial is always, always, always rigged. I shouldn't say rigged because that makes it sound not quite so good. But it's always designed to say, I'm going to match derivatives. Everything is, once you understand that, everything else becomes, all right, I'm cool with that. Why isn't there a half in front of the f sub xy? Well, there's 2 answers. One is, I don't need it, because notice that when I take derivative with respect to x and then take derivative with respect to y, they both have exponents 1. So I'm bringing down a 1 and I'm bringing down a 1. So I don't need to cancel anything. The other thing is you can say, it's actually kind of there. And you might say, no, it's not. Why is it kind of there? Well, what derivative are we missing? Fyx. So one way you can think of it, and we actually are going to touch on this in a second, is that this fxy at ab, x minus a, y minus b, could in some way be thought of as a half fxy at ab times x minus a, y minus b, plus 1/2 fyx at ab, and ran out of space. Okay, but the point here is you could say it is kind of there, and we're going to come back to that in a second. Well, in a second, meaning in about 20 minutes from now. Okay, so let's do some examples. Here we go. Find the second order Taylor polynomial for the function f of xy is 2 e to the x plus y minus sine of xy at 0, 0. Okay, so I'm trying to find the second order Taylor polynomial. Basically, what I know lies ahead for me is many, many derivatives. So I'm just going to be patient and take many, many derivatives. All right, well, in particular, I have to take all derivatives up through the second order. So a good place to start is the first order derivatives. So f sub x. When I take the derivative with respect to x, what will I have?
x plus y.
Well, 2 e to the x plus y. And then? Minus y cosine xy. F sub y will be 2e to the x plus y minus x cosine of xy. Okay, that's my first order terms. My second order terms, fxx will be 2e to the x plus y still. Okay, plus y squared sine of xy. Fxy will be 2e to the x plus y.
yx cosine xy.
Sorry, what?
Yx, or plus yx sine xy.
Well, let's be careful here. We're taking so fxy means we're coming to f sub x, taking the derivative with respect to y. What rule do I need to take the derivative of y cosine of xy if I'm taking the derivative with respect to y? Product rule. So, the derivative of the first will be 1, and I'll have cosine of xy. Then I'm going to take the derivative of the cosine of xy with respect to y. Minus will become plus xy sine of xy. Okay, fyy is 2e x plus y and x squared sine of xy. Okay, good times. All right, now, what comes next? We have to evaluate. Because if we go back to our second order Taylor polynomial, it says, yes, we're taking derivatives, but we're also evaluating everything. And evaluating them where? Well, we're evaluating them at the point. So in our case, what we're going to have is our point is 0, 0. So I need to evaluate everything, including the function itself. Well, what is f of 0, 0? So we plug in 0, 0. 2e to the 0 minus sine of 0 will simplify to be 2. F sub x at 0, 0 will be 2. F sub y at 0, 0 will be 2. F sub xx at 0, 0 will be 2. The whole 2 and nothing but the 2. F sub xy at 0, 0 will be, oh good, there's some variety, 1. Yes? Because, that cosine. Cosine of 0 is 1. F sub yy at 0, 0 will be 2. Okay, so I took all my partial derivatives up through the second order because I needed the second order. I evaluated everything, and now we just plug it in. So again, coming back to the formula, it's the function, the partial derivative times x minus a, partial derivative of y minus b, so forth and so on. A and b is 0, So it's going to be x and y and x squared, y squared, so forth and so on. So if we put this all together, we get the value of the function, which is 2, plus the derivative with respect to x, which is 2, times x minus a, which is x, plus derivative with respect to y, which is 2, times y minus b, which become y, plus 1/2 times the second derivative with respect to x. So 1/2 times 2 will be 1, times x minus a squared, which becomes x squared, plus the derivative with respect to x and then with respect to y, in other words, the second mixed derivative, if you will, which will be 1 times xy, again that's x minus a, y minus b, plus 1/2 times the second derivative with respect to y twice, so that's 1/2 times 2, which will be 1, times y minus b squared, which becomes y squared. And there you go. So, once you know it, you just follow the formula. Yes?
Just to be sure, should f of y have a plus between the two things?
Oh, you're right. It should have a plus. Phew. I don't want to lose any points. Thank you for catching that mistake. Now you might be saying, would you really take points off for that? You should know me by now. Yes, I would. You know, it's not just enough to, by coincidence, it worked out correctly. No, no, no. It's got to be correct. We want it correct. Okay. All right. And now we'll do another one. And same principle. So perhaps in the interest of time, we'll go a little bit faster with this one. What's the main difference between the problem on the left versus the problem on the right? Wait. Yeah, it's shorter. I like that one. But sort of the goal here is to say, look, it doesn't have to be at the origin. And a lot of times we say, oh, we like things at the origin. That's because 0 is such a convenient number to work with. It doesn't have to be. It can be any point we want. Okay, so we're going to go through. So I'm going to write down the function. And you'll notice something. I'm being a little bit lazy here. I did write f sub x. I should have written f sub x of x comma y and so forth and so on. But oftentimes we suppress that notation because it's understood. If you feel comfortable doing that, I'm okay if you do that. If you don't want to do it that way, just write it out. That's okay. So you get f sub x is 2x e to the y. F sub y is x squared e to the y. F sub xx is 2 e to the y. F sub xy would be 2x e to the y. See, the thing is that this is just such a lovely problem because the functions involved are really clean. It's really a function of x times a function of y. And when you take these derivatives, you just say, well, which one am I taking the derivative of? And they're both very simple. So it doesn't take very long for us to write it out. So here are all the derivatives that I'll need. So it's all the derivatives up through the second order. What comes next? Evaluate. Okay, so I'm going to plug in my point. So I'm going to do it for every single one of these. So we'll go ahead and write these all out. You should just keep in mind that there's really not very much difference what we're doing here versus what we did in a previous calculus course. The only thing that's different is now you just have more things to keep track of. And hopefully you'll see that's the theme. Really, multivariable calculus is single variable calculus done multiple times. And so the ideas aren't necessarily new. The procedures aren't really that new either. It's just let's see how do we adapt them to a multiple variable setting. All right, so when I plug in 1, 0 into the function, what will I get? Get 1. F sub x evaluated at 1, 0? 2. F sub y evaluated at 1, 0? 1. F sub xx evaluated at 1, 0? 2. F sub xy evaluated at 1, 0? 2. F sub yy evaluated at 1, 0? 1. All right, and now we do the same thing we did before. We say, okay, so it's the value of the function, 1, plus f sub x, evaluated at 1, 0, times x minus a. So in our case, it's x minus 1, plus f sub y, evaluate at 1, 0, which is 1, times y minus b. Well, b is still 0 in this case, so be y. Plus 1/2 f sub xx, so it'll be 1/2 times 2, which is 1 again. And then I times it by x minus a squared, plus the f sub xy at 1, 0, times x minus a, y minus b, and then plus 1/2 times f sub y at 1, 0, so that's 1/2 times 1, so that'll leave you with a half, times y minus b squared. And there we go. All right, so there's the general idea. Well, what can we do with these? Let's do an example of something we might want to try. Use the second order Taylor polynomial of the function 3x e to the y plus 2y e to the x minus 4xy at the point 0, 0 to approximate f of 0.1, 0.2. So we go back to this idea of approximation. So here's the philosophy. The second order Taylor polynomial, it's an approximation to our function. And so we can get a good guess about what our function is doing. And in some sense, it's a better approximation than the tangent plane because we're using more information. All right. Well, so how do you start this problem? Lots and lots of derivatives. Ah, happy days. 3x e to the y, 2y e to the x, minus 4xy. Okay, so f sub x will be 3e to the y plus 2y e to the x minus 4y. F sub y will be 3x e to the y plus 2e to the x minus 4x. All right. F sub xx will be, okay, so go to the first derivative with respect to x and take the derivative with respect to x again. So derivative of 3e to the y with respect to x, 0. Derivative of 2y e to the x with respect to x, 2y e to the x. Derivative of minus 4y, 0. fxy. Okay, so go to the derivative with respect to x and now take it with respect to y. Well, what do we get? 3e to the y, 2e to the x, minus 4. Now again, you could have gone, say, look, let's start with f sub y and take the derivative with respect to x. You'll get the same answer, unless, of course, we made a mistake. But I'm going to go on the faith that we don't make mistakes, because we're just good. We're getting really good at this stuff. What is f sub y going to be? Sorry, what? 3x e to the y, and what else? Nothing else. Okay, great. Now, we've taken the derivatives. What comes next? To evaluate. And where do we evaluate? At 0, 0. Now, how do we know it's at 0, 0? Yes, it tells us. What if they hadn't told us? What would be a clue that 0, 0 is a good choice? Because 0, 0 is close to 0.1, 0.2. So if they hadn't told us 0, 0, we'd probably say, I want to try 0, 0 because it's close to the point that I'm interested in, and I want to have something I can actually evaluate. All right, so hopefully we're going to get lots of nice numbers. So what happens when I start? What is f of 0, 0? It's 0. What's f sub x at 0, 0? 3, because the y's cause it to disappear. What's f sub y at 0, 0? What is it? I'm sorry? 2. Yeah, because there's that 2e to the x. F sub xx at 0, 0? 0. F sub xy at 0, 0? Well, it'll be 3 plus 2 minus 4. So 3 plus 2 is 5, minus 4 leaves us 1. F sub y at 0, 0 is 0. Which says that our second order Taylor approximation will be 0 plus 3 times x minus a, so that's 3x, plus 2 times y minus b, so that's 2y, 0 x minus a squared, well that's 0, 1 times x minus a y minus b, so that'll be xy, and then 0 times y minus b squared, which is 0. So this right here, this is our approximation. So this is approximately f of xy. And essentially it says, it's almost like the tangent plane, but you have a little bit of extra information. That xy gets us a little bit better approximation. So f of 0.1, comma 0.2 is approximately 3 times 0.1 plus 2 times 0.2 plus 0.1 times 0.2. Well, 3 times 0.1, 0.3. 2 times 0.2, 0.4. So 0.3 plus 0.4 is 0.7. And what is 0.1 times 0.2? 0.02. So it'll be 0.72. So that's what we have. What's the real answer? I don't know. But it's about 0.72. That's what I know because we're using calculus, and that gives us a good approximation. Now let's do a slightly different problem. Okay, so this is parts A and B. Don't worry about part B yet. Focus on part A. So suppose that you have a function f of xy, and it has a second order Taylor polynomial, and it's already given to us. No derivatives are going to be needed to be found, or are they? Well, the second order Taylor polynomial is this polynomial, 3 plus 2x minus y plus 2x squared plus xy minus 4y squared. And the question is, what are the corresponding derivatives for the function f? Well, what can we do? Well, we go back to where is the second order Taylor polynomial coming from? The constant is the constant. The coefficients of x and y would be derivatives with respect to x, and so forth and so on. So, part A, this is a, let's read off the answer. So we want to find f at 0, 0, f sub x at 0, 0, f sub y at 0, 0, f sub x at 0, 0, f sub xy at 0, 0, and f sub yy at 0, 0. That's what we're after. We want those numbers. And I claim we can get them. Because really you should think of this as 3 plus 2, x, you can think of this as x minus 0. And y is y minus 0. X squared is x minus 0 squared. So forth and so on. So, what is f of 0, 0? It's 3. It's this number. What's f sub x at 0, 0? It's 2. F sub y at 0, 0. Negative 1. Okay. F sub x at 0, 0. 4. I was worried I was wondering how many people would forget that there should be a half there. So a half times f sub xx would be the coefficient. Okay, f sub xy. 1. F sub yy. Negative 8. So in other words, if they hand you the Taylor polynomial, then you know information about derivatives. It's sort of similar to what we've done in the past, where we say, here's a tangent line. And like, oh, if I have a tangent line, I know the value of the function, and I know a derivative. It's the same idea, same process. So that's part A. Wow, that was nice. Part B. Well, actually, it turns out for part B, it's a different kind of question, because as it says, g of xy is the Taylor polynomial at 1, 1, not at 0, 0. Now let's find the derivatives at 1, 1. You might say, don't I do the same thing? Well, let's step back for a second. recall this problem from a few minutes ago, where we had this x minus 1 squared. Now, when you're writing out the Taylor polynomial, it really helps to leave it as x minus 1. Because you really want to say, what's the change in x? So that's why you write things as x minus a, y minus b, because you're keeping that change in there. But there's nothing that says that you couldn't have distributed. I could have distributed this and said, oh, that's 2x minus 2. And then I could have put the minus 2 and the 1 together. And I could have done other stuff as well. So, keeping that in mind, coming back to this problem, what happened is somebody found the second order Taylor polynomial and then they foolishly expanded it. And now it's like, oh, all this stuff is now muddled together. Okay, so the question is, how do we recover? Well, the answer won't surprise you. It's to say the following. You know, if I'm looking for the second order Taylor polynomial for f, well, g matches f. That's the way it's constructed. It's designed to match f. So what can I do? Where can I find the right coefficients? And the answer is, find the second order Taylor polynomial for g. Because it's going to match f. And then once we've found those, that'll be the answer. Okay. You understand the philosophy? Well, let's do the problem, and then we can decide whether or not you agree with what we're doing. Okay, so what I'm going to do is I'm really going to say, let's look at g at 1, 1. So g, again, I'm just going to write down 2x minus y plus 2x squared plus xy minus 4y squared. So we look at g sub x. G sub x, well, 2 plus 4x plus y. G sub y, negative 1 plus x minus 8y. G sub x, 4x. Oops, sorry, just 4. G sub x, y will be 1. And g sub y, y will be negative 8. Okay, so I took my derivatives. Now, what happens here is that I can say the following, that f at 1, 1 will match g at 1, 1, and g at 1, 1, I plug it in. 3 plus 2, 5, minus 1, that gets us to 4, plus 2, 6, plus 1 more, 7, minus 4 gets us to 3. F sub x at 1, 1 will match g sub x at 1, 1. And g sub x at 1, 1 is 2 plus 4 plus 1. 7. F sub y at 1, 1 will match g sub y at 1, 1. And g sub y at 1, 1 will be minus 1 plus 1 minus 8. So minus 8. F sub x at 1, 1 will match, f sub xx will match g sub xx at 1, 1, well, which is 4. F sub xy at 1, 1 will match g sub xy at 1, 1, which is 1. And f sub yy at 1, 1 will match g sub yy at 1, 1, which is negative 8. Okay, so if I have my second order Taylor polynomial, I can recover my coefficients, even if they've muddled things up and moved things around. Okay, so now, what does this have to do with optimization? Well, to understand what this has to do with optimization is we're going to look at sort of the second order terms. And I will tell you right now that I'm going to throw a lot of crazy looking math at you. Don't worry too much about it. We're going to summarize it in just a moment. So there's something called the quadratic form. Quadratic just means like second order, like a quadratic polynomial is a x squared. So we're going to look at the terms from the Taylor polynomial that come from our second order derivative. So you have that 1/2 f sub xx at ab times the change in x squared, the f sub xy at ab, change in x, change in y, plus 1/2 f sub y of ab times change in y squared. And the claim is, if you've done anything with matrices, and we really hope you have, because a good algebra course preparing you for calculus should at least have shown you a little bit of matrices, it says that that is actually the same as 1/2 times a vector, which consists of the changes in x and change in y, times a 2 by 2 matrix, where the entries are coming from the partial derivatives of order 2, then times another vector on the end of the change in x, change in y. So why do we care about this particular thing? Well, the answer is, if I'm at a place where my gradient is 0, the f sub x and f sub y term are gone, because they're 0. So that means that this thing is determining my behavior. So I want to understand it. Now, you will take a course, hopefully, in linear algebra. It's a great subject. But when you do, you're going to find out that there's this cool fact, that when you have a matrix here of the form A, B, B, C, B, and A and C are just numbers, then there are two other numbers called lambda 1, lambda 2. They're called eigenvalues. And it turns out that this crazy looking expression can be rewritten as lambda 1 times some combination of change in x, change in y, quantity squared, and lambda 2 times some combination change in x, change in y, quantity squared. Now, where these things come from, this alpha, beta, this gamma, delta, those are, they have a name. They're called eigenvectors. Again, you don't need to worry about that. Here's the kicker. The square tells me that this piece is greater than or equal to 0. And similarly, the square over here tells me that this other piece is greater than or equal to 0. So now, what I have is, since these are greater than or equal to 0, if I can understand those two numbers, then I know what's going on. So here's a summary. If lambda 1 and lambda 2 are both positive, then what that means is that everything is going up, so that the behavior locally has this type of shape. I'm moving up from my point AB. I look like a bowl. If they're both negative, then locally you're going down, which means that you look like an upside down bowl. So from my point AB, I'm going down any way that I go. If one is positive and one is negative, then locally what's happening is that I'm going to have a shape where in one direction I'm going up, but in the other direction I'm going down. So this is called a saddle. And if one is 0, there's just not enough information to figure it out. Okay, so this is why we care about these things, and why they're going to be very, very important when we go into our discussion in our next session. Let me just throw one thing up on the board, and then after that we'll call it a day. Can you do second order Taylor polynomials for functions of more than 2 variables? Yes, you can. That would be for functions of 3 variables. Can you do a third order Taylor polynomial? The answer is yes, you can. That's what you would get. Do you have to do any of these? No. But this is just so, yes, it is possible to do more higher degree order Taylor polynomials. And we'll resume again next time.